All right, so there they are, the gang. Okay, so we had a process that involved drawing a picture, establishing reference axes, drawing free body diagrams, breaking forces into components when necessary, and then applying Newton's second law. I'm going to work you through these first couple of steps, all right? And it starts with this same picture that I already drew. So while I am, in general, not a fan of shortcuts, to save a little bit of time, I'm just going to go ahead and copy and paste that, all right? Because ideally, you have this already. Yes, very good.
There's no shame in that.
The next step is to establish a reference axis. And we have two objects here. Down the road, we're going to discover that there's no need to use the same reference axes for both of these objects. But in this case, we can do it. It makes a lot of sense, and it's almost certainly what you all did. If we think about what's going on here, there is horizontal motion of the cart. There is perfectly vertical motion of our hanging mass. The forces involved, just eyeballing. I don't see any forces that look like they're going to be in any other directions but horizontal and vertical. So it makes a lot of sense for us to use a perfectly vertical and perfectly horizontal axis. And what we'll say is positive is to the right in the x dimension, positive is up in the y dimension. It's important to remember, forces are vectors, they have a quantity and a direction. The force of gravity on these two objects is down. But I just decided that down is also negative along my y-axis. Are those negative forces? No, they're not. There's no such thing as a negative force. But they are forces that are in the negative direction on my y-axis. My cart is moving to the right. That means friction is going to be opposite the direction of motion. Because it's opposite the direction of motion, does that make it negative? Nope. If it's moving in the negative direction, then friction will be in the positive direction. Friction is in the opposite direction of motion, but there's no such thing as a negative force. So how do we deal with that? We use our axes. If friction is aligned with our x-axis, and it is, and it's in the negative direction on our x-axis, then friction is in the negative x direction. Friction isn't negative, no forces are negative, okay? So here is our step one. We've got a drawing, we've got reference axes. Step two on our system was to draw free body diagrams. We need two because we have two objects. I'm going to label the objects M1 and M2 because that helps me keep track of one of the really important forces, which is the weight, and mass shows up in Newton's second law. So we'll need the mass of these two things. It's easier to keep track of which one is which if we call one M1 and one M2, or one MC and one MH for hanging mass. If you just think of them both as being M, you're going to run into trouble. They don't have the same mass. You're going to get equations that have M in them, and you won't remember which one you're talking about. Okay? So let's start with the cart. The cart, well, it's on Earth, so there's a gravitational force. The weight of this object is a force from the Earth's gravitational field pulling straight down on it. The magnitude of that force is equal to its mass times that constant g. G is always positive, so the magnitude of this force is going to be whatever the mass of our cart is, which is 1.3, times whatever g is, which is about 10. The downward force from gravity on our cart is 10 newtons. If we put that cart on a scale that measured in newtons, a force sensor, it would tell us 10 or so. Yeah.
Some forces here.
Yeah, because it's good enough and easier.
Which is why I don't do it.
But if you use 9.8, you're definitely not
The sum
wrong.
of forces variable is
Yeah.
already taken into account gravity.
Our cart is not moving up or
I
down.
don't think we need to
We
add
know
that.
that. which means it's not accelerating. Which means that there's got to be an upward force to balance out this force of gravity. And it has to be the same size. So it's on a surface. Forces from surfaces are perpendicular to those surfaces, which means they're normal. Normal means perpendicular. So there's a normal force acting on this mass. It's straight up. It's got to be equal and opposite to the force of gravity because there's no acceleration up or down. So I'm just going to draw them like that. Like, might as well add that piece of information that I already know.
Let's just go to honestly, I just want to get these two tries. Either the regular class.
Yeah, exactly.
Sure.
Yes. Yep, that's exactly right. And in fact, that's how these electronic balances work. They don't measure mass, they measure force. It's a spring in there. Depending on how much the spring squishes, we know how much force it takes to squish that spring. We also know how much force it will take to, or the Earth's gravitational field will exert on an object of a certain mass. Those things are just doing math. They measure a force, divide by 10. There are two other forces acting on our cart. One is one of the things we're trying to find, which is the tension in our string. The other, we already know. It's friction, which is always opposite the direction of motion. So I know a couple of things. One is, I know that it's moving to the right. We said that. There's no reason that looking at this picture, just the picture itself, doesn't tell us if the cart is moving or in what direction. For all we know, the cart is going to move off up and to the right. Like, if all we had was the picture. But I gave you more information than that. I said, the cart starts at rest or it's moving to the right. I said, it's not going up or down at all. So because of that, we know that there's going to be a force of friction opposite the direction of motion. I also know that the tension force is going to be greater than the force of friction. I know that because it's accelerating. We want it to accelerate to the right at not quite 1 meter per second squared. If these two forces were equal, it wouldn't be accelerating. If the friction force were greater, it wouldn't be accelerating to the right, it would be accelerating to the left. The only way we can get acceleration to the right is to have tension greater than friction. The overall force is to the right, which means the acceleration will be to the right. Okay? This is our free body diagram for the first mass. For our hanging mass, it's only experiencing two forces. There's nothing going on horizontally. It's not moving horizontally. There's nothing pushing or pulling on it horizontally. No force, no acceleration. So all we need to do is worry about the two forces that are there. One of them is the force from the Earth's gravitational field. It's being pulled down. How hard is that force? This hard. Oops, I wrote the wrong number there, sorry. It's being pulled down with a force equal to its mass times g. We don't know what its mass is. We knew for the cart is 1.3 kilograms. So we know the weight of the cart is about 10 newtons, or about, 13 newtons. But we don't know how much mass we're going to put over the pulley to get this thing to accelerate. So we don't know what this number is, but we know whatever it is, it's going to be equal to this object's mass times g. But that's not the only force acting on it. The string is attached to it too. The string is pulling up with a certain amount of tension. Here's some things that are kind of interesting. Number one, because of the way the tension works, we know that this tension and this tension have to be the same. They have to be. The string itself is transmitting that pulling force from one end to the other. So whatever we find needs to pull the cart to the right will also be pulling up on the mass. The other thing that we know is a little bit trickier, but still pretty intuitive, and that is the weight of this object has to be greater than the tension. It's not a balanced set of forces. This weight has to accelerate. How do we know? Because the cart is accelerating. If the weight weren't accelerating, if it were motionless, for example, then the cart would roll forward and the weight would just hang there. That doesn't make sense. If it were moving at a constant velocity, then as the cart sped up, because the cart's accelerating, the string would bunch up, right? The hanging mass would be moving down at a constant rate, the cart would be going faster and faster. That's not happening. We know it's not accelerating faster than the cart because the string isn't stretching out. Like, this is one connected object. However far the cart moves, the mass will move. However long it takes, mass will take the same amount of time. That means all of our kinematic quantities are the same for the cart and the mass. The direction of motion is different, but the magnitudes are the same. They will have the same displacement in a certain amount of time. They will have the same average and instantaneous velocities. They will have the same average and instantaneous acceleration. They have to, because they're effectively connected. So that means my tension force is a little bit smaller than the weight of this object. So we have some connections here mathematically. The tension acting on the cart, pulling it to the right, is the same as the tension pulling up on our hanging mass. And the acceleration of the cart to the right is the same as the acceleration of the hanging mass down, right? So that's on our list of steps in the process. That was step 2. Step 3, look at the forces and make sure that any forces that are not lined up with this coordinate reference axis are resolved into components that are. This is a relatively simple scenario because none of these forces is at an angle to our x or y axis. The normal force on the cart is in our positive y direction, the weight of the cart, negative y direction. Tension on the cart, positive x direction, friction on the cart, negative x direction. The tension on the mass is in our positive y direction. The weight on the mass is in our negative y direction. So we don't need to do any trig here. We don't need to do any sines or cosines. Which means the next step, and this is where I'm gonna abandon you temporarily. Our next step is to use Newton's second law. And when we use Newton's second law, we have to use it for each object.
Where's the supercart's at?
Hang tight. In each direction. The way Newton's second law works is you can definitely use it overall. You can think of forces as being 2 or 3 dimensional. Or we can look at one axis at a time. The math is way easier if we look at one axis at a time. All right? So that's like part 2 of my talking today. I'm going to leave you here and see where you can get. And then there's going to be one more piece that I'm going to give you before the end of the period.